Welcome to Physical Chemistry. We're beginning Chapter 1, Section 1. Now there are several different types of sciences here. Biology, it usually doesn't use a whole lot of math, but it has really complex systems. Chemistry uses slightly more math and slightly less complex systems. For comparison, mathematics, it uses a lot of mathematical sophistication, but usually pretty simple systems. And then physics, compared to mathematics, uses maybe a little bit less math, but slightly more complex system. Physical chemistry, you have quite a bit of both. You have somewhat complex systems, but also quite a bit of mathematical sophistication. Now, Gilbert Newton Lewis said that physical chemistry is everything that is interesting. Our definition, physical chemistry is using mathematics and the laws of chemistry to model bulk matter. Now, the book we're using is roughly 60% mathematics, 30% physics, and 10% chemistry. Now, Chapter 1 deals with properties of matter. Properties can be microscopic or macroscopic. Microscopic properties are properties of atoms and molecules. This is also called chemical physics, and it's highly mathematical. Now, what some of the stuff that you might study under microscopic properties would be the size of a molecule, or the shape of a molecule, the velocity of a molecule, the momentum of a molecule, or intermolecular forces, such as London dispersion force, Debye force, and Keesom force. Now, macroscopic properties are properties of bulk matter. Examples would be temperature, pressure, and viscosity. Physical chemistry has four main components. Component meaning category or branch. One is thermodynamics, and this is purely macroscopic. This is what we're going to be starting out with this year. Two is quantum chemistry. This is microscopic. This could also be called quantum mechanics. We're going to be getting to that later on. Three is statistical mechanics. This is the bridge from microscopic to macroscopic. We're not going to be doing a whole lot of this. And then four is kinetics. This deals with the rate of processes, such as the rate of reaction or the rate of diffusion. This is highly mathematical, and we'll be doing a few chapters on kinetics. That's the end of Chapter 1, Section 1. Now we're in Chapter 1, Section 2. Thermodynamics. Thermo comes from the Greek word for heat. Dynamics comes with the Greek word for power. Now, there are two types of thermodynamics. One is equilibrium thermodynamics, or just thermodynamics. Equilibrium dynamics or equilibrium thermodynamics. That basically means exactly what it is. The system is in equilibrium, and this is what we're going to be covering almost exclusively. There's also irreversible thermodynamics, which means the system is not in equilibrium. We will be briefly mentioning this on occasion, but not a whole lot. Now, there are several categories of equilibrium. The first is mechanical equilibrium. Mechanical equilibrium means that there is no net force acting on the system. So remember, the forces add up. So you can have a whole bunch of forces, but if they basically cancel out, you have balanced forces. If you have a bunch of forces, they're not all equal, so they cancel out. You have an unbalanced force, or a net force that's non-zero. So if you're in a mechanical equilibrium, there's no net force. Therefore, the system has no acceleration. The second type of equilibrium is material equilibrium. Now, this means that there is no net chemical reaction in the system, or no net chemical transfer, or no net transfer of matter. You can still have matter transfers, just that the rate of the matter coming in has to be exactly the same as the matter coming out. And then the third type of equilibrium is thermal equilibrium, which means no net heat transfer, or all parts of the system are at the same temperature. Now, thermodynamic equilibrium means that the system is in all three types of equilibrium. Thermodynamic equilibrium means the system is mechanical equilibrium, material equilibrium, and thermal equilibrium. Now, our system is whatever part of the universe that we are interested in, whatever we're analyzing. It can be the contents of a test tube, a fractionating column, or a biological cell. It can be any scale. It can be really small or really large, just whatever you want to analyze. Now, your system can be open. Open means that it allows transfer of energy and matter. So here's our system surrounded by a wall. We can have matter coming in, energy coming in, matter leaving, energy leaving. That would be an open system. And these don't have to be the same rate at all. That would be the whole point. The system can also be closed. Closed means it allows transfer of energy, but not matter. Or you can have a system that's isolated, which means no transfer of matter and no transfer of energy. Now your system is surrounded by walls, and then beyond the walls is whatever the walls interact with. That's the surroundings. So our system plus the surroundings, and the walls of course, is our universe. We normally neglect the walls except to describe how the walls behave. Now there are several types of walls. Now one, they could be rigid versus non-rigid. A rigid wall means it can't move. A non-rigid wall means that it can move. Also, it can be permeable or impermeable. Permeable means matter can pass through, such as a cell membrane. And keep in mind, though, that a membrane can be selective. Like there are membranes that allow water to pass, but not certain other substances. That's how water filtration can be done. Impermeable means matter can't pass through. And also, walls can be adiabatic versus non-adiabatic. Adiabatic means there is no transfer of energy, such as heat. Non-adiabatic, which is the same as diathermic, means that energy can pass through. Now let's talk about a few examples of thermodynamic properties. One, of course, is composition. What is your system made of? Sometimes that's important and sometimes it's not. You just have to pay attention to what you're trying to do. Another thermodynamic property is pressure. The symbol for pressure is capital P. Another thermodynamic property is temperature. The symbol for temperature is capital T. Another important thermodynamic quantity is internal energy. We're going to be talking about a whole bunch of different types of energy in thermodynamics, and one of them is internal energy, and the symbol is capital U. Also, entropy, which is capital S, and then volume, which is capital V. Now we're also going to be using V for potential energy. So by context, you have to pay attention to, okay, is this time capital V volume or is it potential energy? It can get confusing, but there's only 26 letters in the alphabet, so we have to do something. Now property can be intensive or extensive. An extensive quantity depends on size. If the system gets larger, the value gets larger. For example, volume, mass, or heat. If you add more, if you increase the volume, the value of the volume increases. Same thing, if you add more mass, the value of the mass increases. If you add more heat, the value of the heat transfer increases. Now for comparison, there's intensive, which is independent of how much. For example, density, temperature, or pressure. If you have a pile of gold at one density, you add some more gold, the same density. Same thing, temperature. If you have a bucket of water at one temperature, you add another bucket of water at the same temperature, the double-sized bucket has the same temperature as before. And then same with pressure. If you have one hot air balloon full of air at one pressure and you add another hot air balloon full of air at another pressure, the two balloons, they got the same pressure still. That's why intensive quantities are much more important than extensive quantities. It makes them much more convenient to work with in many cases. So anytime that you're given a quantity or you calculate a quantity or whatever, you think about it. Is this quantity intensive or extensive? Now systems can be either homogeneous or heterogeneous. Homogeneous or homogeneous means uniform. Now we haven't defined phase yet, but we will. But the system has one phase, and it can apply to a mixture, such as one substance, a solution, such as Kool-Aid. You have sugar and water and so on. If it's all mixed well, it's all dissolved, you've got a homogeneous system. And what's most important, though, about a homogeneous system or homogeneous system, all your intensive variables or all your intensive properties are constant. If you've got one big bucket of water, it's homogeneous, then the temperature is the same throughout, the pressure is the same throughout, density is the same throughout, etc. This is very important. We'll mostly be talking about homogeneous systems, especially in thermodynamics. Now for comparison, you can have a heterogeneous system, which usually means more than one phase. For example, in chemistry, you might know that oil will float on water. That's because oil has a different density than water. So density is an intensive quantity. So you're going to have two different intensive quantities because you have two different phases. Now let's define state as in thermodynamics. The state of the system is determined when we specify values for the minimum number of intensive variables. Extra would be redundant. For a pure homogeneous material, this number is 2. Now, we haven't even defined really why that is or anything. We're going to be doing the calculations for that later on. This is sort of an introduction. But example would be like composition and temperature. And of course, we're assuming no external field. That's part of mechanical equilibrium. Okay, that's all for Chapter 1, Section 2. Now we're on Chapter 1, Section 3. We're going to talk about temperature. Temperature is a most important intensive quantity. The reason is the temperature is the property that tells us the direction of energy flow. You know, the energy is going to flow from the hot to the cold, the higher temperature to the lower temperature. Now, some would argue we can't actually measure temperature directly. For example, when you're looking at a mercury thermometer, you're looking at actually the volume of the mercury. The volume of the mercury has changed because the density of mercury has changed based on temperature. So it's really an indirect measurement, but that's sort of a technicality. Okay, that's all for Chapter 1, Section 3. Now we're in Chapter 1, Section 5. We're going to talk about gas laws. This is the equation of state for an ideal gas. Now, later on, we're going to show an ideal gas is also a perfect gas. We'll be defining that later on. But this is our ideal gas. PV equals nRT. Pressure times volume is equal to the number of moles times R times temperature. Now, R is our universal gas constant, and it can be equal to different numbers depending on what unit system you're using. For example, it can be 0.08206 liter atmospheres per mole Kelvin. It can be 1.987 calories per mole Kelvin. It can be 8.314 joules per mole Kelvin, or it can be 82.06 centimeters cubed atmospheres per mole Kelvin. Now look at this. These all have denominators of per mole Kelvin. So what that tells you is that it's intensive because we're dividing by the size of the system. But more importantly, notice joules and calories, they're both units of energy, Therefore, it stands to reason that liter atmospheres is also a unit of energy, and centimeters cubed atmosphere is also a unit of energy. So that's why I was saying down here. Liter atmosphere is a unit of energy which we'll use, and centimeters cubed atmosphere is also a unit of energy. Now R is called the universal gas constant, although we will see it sometimes in equations that have nothing to do with gases. It's actually a little more important than just gas constant. Now, for a real gas, PV equals nRT is somewhat true as long as you're at low pressure and high temperature. The reason is it ignores intermolecular forces because at low pressure or high temperature, the molecules are so far apart you don't really have any intermolecular interactions. And likewise, it assumes the molecules actually take up no space. Okay, that is it for Chapter 1, Section 5. Now we're in Chapter 1, Section 7. So, we just talked about the ideal gas law. Now we're going to talk about a real gas law, the van der Waals equation. The van der Waals equation is an example of a real gas law. So instead of just PV equals nRT, we have pressure plus AN squared divided by V squared, this is still volume, times volume minus NB, that's the lowercase n, lowercase b, equals nRT. Or solving that for pressure, we get P equals nRT over V minus NB minus AN squared over V squared. So these symbols all mean the same thing as before. P is pressure, V is volume, N is the number of moles, R is the gas constant, and T is temperature. But A and B are gas-specific constants because not all gases behave exactly the same. So A is called the pressure correction term. Now we're subtracting out the pressure because intermolecular forces are always attractions, which reduces pressure on the wall. So if you think about it, if you have an ideal gas, you have all the molecules bouncing around inside the container. Then a real gas, the molecules would attract each other, so they're not pushing on the walls of the container quite as hard. Now the B term is due to the size of the molecules. Remember, we said with an ideal gas, we assume that the molecules don't actually take up any space. This B term corrects for that because real-life molecules do take up space. Now, like I said, the ideal gas law works at low pressure because it assumes the molecules have no volume, but at high pressure, intermolecular forces become relevant. Now let's talk about pressure, volume, and temperature behavior in the condensed phases. I spelled condensed wrong, but anyway. Now remember, the condensed phases are solid and liquid. Now for any substance, we could say that volume is a function of temperature and pressure. Now we're assuming that N is constant, of course, because we're not having any reaction. So like I said, we haven't defined this F yet, but it's just some function. Could be different for every gas or something. We don't know yet. Now remember from calculus, differential calculus, that d, lowercase d, is differential. Just like delta means a finite change, d, the differential, means a infinitesimal change, an really tiny change. So, for example, dV would be the differential of volume. Now, since we said that volume is a function of temperature and pressure, we have to write our differential as a function of temperature and pressure. So we're going to say the differential of volume is the partial derivative of volume with respect to temperature holding pressure constant times the differential of temperature, plus the partial derivative of volume with respect to pressure holding temperature constant times the differential of pressure. So remember, this lowercase, or this subscript p here means constant pressure, and this subscript t here means we're at constant temperature. Now this here, when we do it like this is called the slope formula. And we can do this because this is the total differential of volume. And remember, volume is extensive, so even this differential is still extensive. What we're going to do now is we're going to divide this equation by volume. So now we have the differential of volume divided by volume equals 1 over volume times the partial derivative of volume with respect to temperature holding pressure constant times the differential of temperature, plus 1 over volume times the partial derivative of volume with respect to pressure holding temperature constant times the differential of pressure. Since we've divided by volume, this version is intensive. Now remember, you can cancel out the v's here, but then you'll just be back where you were before, which was extensive, which is not what you want. So it's important to remember, you can take the ratio of two extensive variables and end up with something intensive. That's a good idea sometimes. Now this here is supposed to be a rho, a lowercase rho. So rho, remember, is density, mass divided by volume. Remember, mass is extensive, volume is extensive, but rho is intensive. So that's an example of what I was saying, where you can divide two extensive quantities and end up with an intensive quantity. Now this squiggly line here is the Greek letter alpha. We're going to call it the coefficient of thermal expansion, also known as thermal expansivity, or the cubic expansion coefficient. Now alpha is going to be equal to 1 over volume times the partial derivative of volume with respect to temperature holding pressure constant, which basically means it's this much over here. That works out to being the same as 1 over the molar volume times the partial derivative of molar volume with respect to temperature holding pressure constant. So remember, capital V with a subscript lowercase m is molar volume. So molar volume is just our volume divided by the number of moles, which obviously makes it extensive divided by extensive, intensive. Now this is supposed to be a kappa, not a K. Hopefully we can keep track of the difference somehow. Kappa means isothermal compressibility. Now we're defining minus K is equal to 1 over volume times the partial derivative of volume with respect to pressure holding temperature constant. Now K is equal to, like I said, we would just move the minus sign over here. So K is equal to minus 1 over volume times the partial derivative volume with respect to pressure holding temperature constant. And that is equal to minus 1 over the molar volume times the partial derivative of molar volume with respect to pressure holding temperature constant. So because of these equations we ended up we got alpha is a function of temperature and volume, and kappa is a function of temperature and pressure. Now alpha and kappa are both intensive. Now for solids, alpha is a range of maybe 10 to the minus 5 to 10 to the minus 4 per Kelvin. For liquids, alpha is a range of maybe 10 to the minus 3.5 to 10 to the minus 3 per Kelvin. And for gases, alpha is a range of maybe 10 to the minus 3 to 10 to the minus 2 per Kelvin. For solids, kappa is a range of maybe 10 to the minus 6 to 10 to the minus 5 per atmosphere. For liquids, kappa is a range 10 to the minus 4 to something, not even sure, per atmosphere. And then for gases, kappa is a range of maybe 0.1 to 1 per atmosphere. Liquid is the most complicated phase, which is why we don't really have a number for that. Okay, we're still in physical chemistry, chapter 1, section 7. So let's talk about the volume change that occurs when we have 50 centimeters cubed of argon, which we're going to treat as an ideal gas, is heated through 5 kelvins. We're going to start at 298 kelvins, and we're going to keep pressure constant. Remember, capital P is pressure. So we're going to start out with that slope formula, the extensive version. The differential of volume is equal to the partial derivative of volume with respect to temperature holding pressure constant times the differential of temperature plus the partial derivative of volume with respect to pressure holding temperature constant times the differential of pressure. Now remember, we said constant pressure. If pressure is constant, the differential of pressure is 0. 0 times anything is 0. So this whole term is equal to 0. So that's the differential form. That which would mean an infinitesimal change. We want a finite change. So we want delta V. Delta V means the finite change in volume. So what we're going to do is we're going to basically say, okay, delta volume is roughly equal to the partial derivative of volume with respect to temperature holding pressure constant times delta T. So that's going to be roughly equal to alpha times volume times delta T, change in temperature. Now we're going to use, we're given that we're going to treat it as an ideal gas, so we're going to substitute in PV equals nRT. So remember, alpha equals 1 over V times the partial derivative of V with respect to T holding P constant. So substituting in for the volume here, we get 1 over volume times the partial derivative of nRT over P with respect to temperature holding pressure constant. So then we just pull out the constants, nR and the P, and we get the derivative of T with respect to T, which is just 1. So we get 1 over V times nR over P, substitute using PV equals nRT again, and we just get 1 over T. So what that tells us is that for an ideal gas, alpha is just 1 over temperature. Now, back to the example though, then we're going to say delta volume is roughly equal to the partial derivative of volume with respect to temperature holding pressure constant times the change in temperature. So we substitute that in, we get 1 over temperature times volume times change in temperature. So we have 50 centimeters cubed times 5 kelvins divided by 298 kelvins. So the answer is about 0.84 centimeters cubed. Now, these apply to solid, liquids, or gases, always. Alpha is 1 over volume times the partial derivative of volume with respect to temperature, holding pressure constant. Kappa is minus 1 over volume times partial derivative of volume with respect to pressure, holding temperature constant. But these only apply to ideal gases. Alpha we just showed is 1 over T. Kappa is 1 over P. Let me show you how that is, because it's also mathematically tricky. So let's do isothermal compressibility of an ideal gas. So kappa is minus 1 over volume times the partial derivative of volume with respect to pressure holding temperature constant. So we start with PV equals nRT. We solve for volume. We get V equals nRT over P. So we're going to substitute that in up here. So we get kappa is minus 1 over V times the partial derivative of nRT over P with respect to P holding temperature constant. So we'll just go ahead and pull out the constants then. Remember, we're constant temperature, and R is a constant for real, and then we're holding the amount of material constant because there's no reactions or anything. So we get kappa is equal to minus 1 over volume times nRT times the partial derivative of 1 over P with respect to P, holding temperature constant. So we use PV equals nRT again. This time we solve for pressure. We get nRT over volume. So we're going to substitute that back in over here. So we just get kappa is equal to minus P times the partial derivative of 1 over P with respect to P, holding temperature constant. Now hopefully you remember the power rule from calculus. We get kappa equals minus P times minus 1 over P squared. We're going to cancel those extra P's, and we just get kappa is equal to 1 over P. Okay, we are now done with chapter 1.